This next section is on the Doppler shift. It's section 14.4. And the Doppler shift is something that's familiar to all of us, because if we pass a train, or if we're just sitting still, here we sit, train goes by, then as the whistle blows, as it approaches us, we hear a higher frequency, and then when it recedes and goes away from us, we hear a lower frequency. That is because as the wave comes toward our ear, it is squeezed together, therefore giving us a higher frequency, because the train is moving toward us, so it's pushing each wave on top of the other one in front of it. As it's going out here, it's stretched out more, so it's a lower frequency. So what we always hear as something approaches us, then goes away, is a higher frequency than a lower one. Da. The same goes for a race car that's passing us. So these race cars and these trains pass us, it always goes from high to low, never the reverse. What is that shift in frequency? Well, you'd be amazed to know that if you have perfect pitch and you go to a racetrack and you can detect the frequency change in terms of musical notes that represents, you can determine the speed of the car. Kind of amazing, huh? How do we do that? Well, it turns out that there are two formulas. One is for the Doppler shift when the observer is moving toward the source. The other one is when they're moving away from the source. So this is the frequency that the observer sees. It's the frequency of the source. That would be the train or the car or the horn or whatever, times 1 minus V naught over V. V naught's the velocity of the observer. V is the velocity that the object is moving, divided by 1 plus V of the source over V. So put that parentheses in the wrong place. This is where observers toward the source. Observers toward the source. Then we have another one where the observer is going away from the source. Observer's going away from the source. And that is F naught is equal to frequency of the source times 1 plus V naught over V divided by 1 minus Vs over V. And you'll notice here that the signs are exactly inverted, whereas this is minus, this is plus, where this is plus, this is minus. So they're kind of hard to keep straight, but using these, you should be able to easily compute that if you have a velocity of a source, a velocity of an observer, and a velocity of a source. In other words, this allows actually the observer to move at the same time as the source. And the object is moving at a velocity v, this will give the change in the frequency. The observed frequency versus the natural frequency of the system. So if the car horn or the train whistle is giving this frequency, what you're going to hear is given by this equation. If the observer is going toward the source, here if it's going away.